Recording has started.
All right, let's continue. So I think the next step is to visualize those equations by drawing this kind of plots. So this is also very important in this course. There are two types of the IDVD or IDVG curves. So basically, we want to visualize those equations by drawing this kind of plots. The first one is ID versus VD, and sometimes we call this output curve or output characteristics. It's output. And this is ID versus VD. But you know, this is a function like ID is a function of the F, let's say VG and VD. So if you think about the equation here, in the linear region, you have ID, and then the variable will be VG and VD. So you have two variables. But when you draw this 2D plot, you can only choose one variable here. So if you choose VD, you draw ID VD. Then the VG will become a control. So we have a group of curves corresponding to different VG. This is because you choose VD as a variable. And then the VG is a control. So this is how it looks like. This is exactly the same as the equations in the previous slide. So when the VD is small, so here this is ID VD. So when the VD is small, so let's say VD is small, you know it's in the linear region. For example, if we give a certain VG, look at this VG, maybe this VG is like, for example, 1 volt. So we have a given VG. Then first, the transistor is in the linear region, and it will follow the equation. Which equation? This equation. This linear region equation. And you see ID actually is a second order function of the VD. In other words, in the plot, you will expect a parabolic function. So here is a parabolic function. This is exactly described by that equation. And then here we see the turning point. The turning point, as we discussed, is the turning point between the linear region and saturation. And at this point, the VD equals to this VG minus VT. If the VD is larger than this VG minus VT, then the transistor enters the saturation, and then saturation means saturated current, flat. So this is how you draw this ID-VD curve. But this is just for one given VG. If you change the VG, then the saturation current will change. Why? If you look at the equations here, for the saturation current in the saturation, here does not depend on the VD, but the current depends on the VG, actually squared. So as you increase the VG, you can imagine that the saturation current will increase. So you get a group of curves like this, corresponding to different VG. And then the turning point here, if you draw a dashed line, connecting those turning points, you get a boundary between the linear region and the saturation region. So here in this plot, where is the cutoff region? Cutoff region is when the VG is smaller than the threshold, then it's almost a 0, so you cannot see it. So it's basically along the x-axis here. That is the cutoff. Any questions? Okay, so this is ID-VD. And then we can look at IDVG again. So here we have this ID as a function of VG and VD, but now we want to choose VG as a variable and VD as a control. So here we draw ID versus VG. And if you use the equations earlier, then you will expect this kind of curve. So first, we need to pass the VT. And below the VT, this is the cutoff region. The current is almost 0, and you cannot see it here. And above the VT, then we have the current. But then we need to determine the turning point between the linear and the saturation. So here, actually, the turning point is here. Why? So from the VT to this turning point, we are increasing the VG. That means the VG actually is sweeping from small to large. So initially, the VG is small. So that means it's smaller than this VD. If it's smaller than the VD, then you know in this region is the saturation, because VG minus VT smaller than VD. So this is saturation. And then you keep increasing VG. Eventually your VG minus VT will be larger than the VD. Then this is a linear region by definition. So this is the turning point. And here I have two curves because we have two VD. Because VD is a control in this case, we have two curves corresponding to two VD. And you can see here VD, the case 2, is larger than the VD of case 1. And the turning point is here and here, respectively. Any questions? So I would say those 3 pages are very important. The equations here, of course, later you are going to use this to calculate the current. And then also visually, the IDVD curve and IDVG curve are also important. Alright, next we are going to discuss the MOSFET from the band diagram point of view. We like band diagram, as you can tell in this course. So here we show the 3-dimensional view, and we show the MOSFET structure, but we rotate by 90 degrees. We lay down the MOSFET, and then we lay down it horizontally. So here the surface of the silicon actually is this cross section, and then the MOS is along this X direction, and then the channel is still from the Y direction here, and the Z direction here is the W of the channel. So here, let's show the band diagram at the equilibrium state, where the gate voltage and drain voltage both are 0. So in this case, from the source to the drain, we have the NPN kind of doping, and we discussed in the lecture 7. It's more like a two back-to-back PN junction. So we have those two barriers here. And for the source and the drain, N-type doping, that means we have the electrons there, a lot of electrons, majority carrier electrons. And in the channel region, it's P-type. So if you do nothing, then the holes are very minimal. It's minority. And there are many holes here. Electrons are by minority, holes are majority. So you don't have electron basically here. And then if you apply the gate voltage, but keep the drain voltage 0, So this positive gate voltage applied here will bend down the band towards the surface of the silicon. So that's why here the gate voltage is going to bend down the band. So if you recall the last lecture 8, we draw this kind of MOSFET band diagram, something like this. When the gate voltage is larger than the threshold, then we see that the gate voltage is going to bend down the band, and then the surface is inverted to electron. So this band diagram is actually showing the cross section in this 3D view like this. So this is a cross section with let's say the X and Z direction, what we draw in the last lecture. So we have electrons basically towards the surface. That is a channel here. So you see you have electrons in the channel. But the electrons will not move because the drain voltage is 0. So you have equal potential, source and drain. Now if you further increase the drain voltage, the drain, positive voltage push down the drain band. Now you see a slope from the source to the drain. And then, as we discussed many times, electrons, like water, will fall down along the slope. So that's why the electrons will move over this barrier and then fall down the slope and then collected by the drain. So this is your electron flow, and then the current can conduct in this case. So this is how you describe the MOSFET operations using the band diagram. Any questions? So let's have a recap on the Fermi function. So we discussed that the Fermi function will have the EF Fermi level, and then the Fermi level is typically within the band gap. But here in the conduction band edge, EC and above, we have small probability of electrons being filled, or electrons can occupy those energy levels. But the probability is like a Boltzmann approximation, is an exponential decay function here. Then let's look at the band diagram along the channel direction. Okay. So we basically just look at one slice of this 3D band diagram. If you only look at this cross section, the Y and Z direction. So that is here from the source to the channel and then to the drain. So we have the NPN, and here we have two PN junction, and we have those two built-in barrier in the PN junction. So this is the equilibrium state. We have a single Fermi level without the drain voltage. And then what the gate voltage does to the band diagram is to push down the band in the channel, because gate voltage is applied to the gate, which is above the channel. So then if you apply the gate voltage, you are going to push down the band. The barrier from the source to the channel will be reduced. So this is a key. Okay, this source to channel barrier is a key, this one. So this is because the distribution of the electrons in the conduction band, we have this exponential decay function here. If the barrier is high without applying gate voltage, then you almost have no electrons at this high energy level that can move over the barrier. But if the gate voltage is applied, then we push down the band. Now you have many electrons above this barrier. So if you apply drain voltage, then those electrons will fall down along the slope. So the key conclusion here is that the gate voltage modulates the source to the channel barrier. That is controlling the current. And now if you apply the drain voltage here, then we think about this process. We have a lot of electrons in the source, but before you apply the gate voltage, the source to channel barrier is high. Even though you have drain voltage, then the electrons that are over the barrier is limited. But now if you apply the gate voltage, then we push down the band. You have more electrons that can move over. Then you will have the drain current. So ideally, for the non-channel transistor, only the gate voltage can control the barrier height here for the source to the channel. Only the gate. Only gate voltage control this barrier. This is true for the non-channel device. When the L is large, for example, micrometer scale. Why is that? Because the drain is far away. If the L is large, that L is in the same micrometer. So the drain voltage, even you change it here, it will not affect the barrier height for the source because it's so far away. So the ideal transistor is a gate controlled device only. So only the gate can turn on the switch and you can have the current. This is true for the non-channel device. And let's look at the conduction band at various biases for this non-channel device. So this is what we discussed before. If we don't apply the drain voltage, source and drain will be the same potential. And then when the gate voltage is 0, then we have a large barrier. But when we apply the gate voltage here, then we push down the band, then the barrier height is reduced. Then we have the electrons move over if we apply the drain voltage here. So the electrons now see a small barrier, and then if you have a little bit small drain voltage, then the electrons can fall down this slope. So actually small drain voltage, this is a linear region. And we can consider the saturation region when we have a large drain voltage. So if this drain voltage is large, so the difference here is that you will have a large drain voltage to push down the band towards the drain. But the saturation will happen because even though you have a steeper slope here with larger drain voltage, if you further increase the drain voltage, then you are going to have an even steeper slope. But the source determines how many electrons can be over the barrier. And then of course with a steeper slope, they will fall down faster, like the velocity will be larger by the larger drain voltage. but the number of electrons determined by the source. So even though you have very large drain voltage eventually, then the number of electrons is limited by the source. So that means the current will be saturated, even though they can move fast, but the number of electrons are limited in this case. So that's why this will have the saturation. This is true for the long channel device. Okay, when the drain is far away from the source, this L is large. So here you push down the drain band edge, it will not affect the source barrier because they are far away. So this is for the non-channel device. And then let's summarize for the non-channel device. What matters is this barrier between the source and channel. And this barrier is only controlled by the gate voltage. So ideally, the MOSFET are the barrier controlled devices here, and this barrier is modulated by the gate voltage. So if you summarize what is MOSFET, MOSFET is a barrier control device, and the barrier height is modulated by the gate voltage. But in the short channel transistor, for today's transistor, for example, here only like less than 20 nanometer, then the drain voltage will affect the source barrier. So here if you apply large drain voltage, VDS, you push down the drain band, but the source barrier here will also be reduced. The reason is that they are so close. So the drain voltage can affect the source barrier. So the VD lower the source to channel barrier. Then you will have more current flow over. If you further increase the drain voltage, that means what? It means the current will no longer saturate, because as you increase the drain voltage, then the barrier height will further decrease. Then you have more electrons move over, and then the current will further increase. So the saturation region no longer saturates. So that is a key difference in today's short channel transistor compared to the long channel transistor we derived earlier. So let's look at the real example. So this is measured from the real chip for L equals to 100 nanometer device. This is typical in the 2007. And this is ID versus VD. Sorry, ID versus VD. And this is the real data from the measurement. And we see a group of curves corresponding to different VGS, similarly as before. But if you compare what we showed earlier, we have this child region, and then it will become flat. This is what we predict for the long channel. But in the real device here, we see that the current further increase. This is because the drain voltage here will reduce the barrier height of the source to the channel. So you have more electrons jump over, larger current, larger drain voltage. So in this course, we will, let's say, use those ideal equations to calculate the current. And this is good for the non-channel device. And we're not going to discuss the IV equations for the short channel. Actually, there's no analytical equations as simple as this to describe the short channel IV relationship. So for the short channel, what we require is a conceptual understanding why the current no longer saturates in the short channel device, and then the IDVD curve with the slope here can represent the short channel transistors behavior. So any questions? Okay, so I think one more comment on the IDVD curve. I think I forgot to mention this. Let's go back to here. So why the linear region? Okay, so the linear region tells that the drain voltage is small. If the drain voltage is small, that means we are looking at this region. The drain voltage is small. So you can see that here, if you draw a straight line, it can approximate the IV relationship at a very small drain voltage. If this is a straight line, that means linear. And if the IV is linear, that means it's a resistor. So in other words, in the linear region, if the drain voltage is very small, you can approximate the transistor as a resistor. That's why this is called a linear region, when the VDA is very small. All right, I think the take-home message today, first, the key conclusions, those equations, and understand the meaning of each parameters here. And we don't require the derivation for the equations here, but I think a concept like the cross-section touch density here multiplied by the velocity give you the current. If you understand this, then that will help you to understand how we reach the current equation in the linear region. And the second is the IDVD curve, and determine those regions and the turning points. And third one is this IDVG curve, and also the turning points. And then lastly, understand why the short channel transistor today no longer saturates the current. This is because the drain voltage can lower the barrier between the source and the channel. All right, any questions before we stop here? If no, I think we can end today's lecture here. Thank you.